Section 15.1, double integrals over rectangular region. Remember from first semester calculus when you had definite integral, that was like antiderivative evaluated at upper limit minus evaluating the antiderivative at the lower limit. That was fundamental theorem of calculus. However, the definite integral was performed over a closed interval. So that means x had to go from a to b on a number line. And the way we approximated the area under the curve, provided f of x was a positive function. So we kind of approximated by taking these rectangles. So we divided the area under the continuous curve into sub-intervals, and we added the areas of these rectangles. And let's say x sub I was a sample point. So therefore, if you would take a typical rectangle, so the height would be like f of xi. Let's say you are at xi, and the ith sub-interval, that is. And then you multiply it by the, the area of the rectangle is length times width. So that would be fxi of xi times delta x. And if you add up all these areas, that would be approximately the same as the value of this definite integral, provided f of x is a positive number. However, the method which we approximated, they were like left endpoint, right endpoint, and midpoint. And this summation was called Riemann sum. So in order to make this approximation equal, so we had to take the sum of all these rectangles and n many of them, and let n to approach to infinity, where delta x, the width of each of these rectangles, would be b minus a over n, and xi would be a plus I delta x. So as I said, provided the function is positive, then this guy would represent the area of the curve. If it is not positive, then depending on the content of the problem, it could mean anything else. However, in third semester calculus, you have double integral over a closed area, not a closed interval, but a closed region. So the region can be as simple as a rectangular region, or it could be any general region, which we'll examine that in the next section. So what happens is the following. So remember here, we divided the x-axis into sub-intervals equal width. In function of two variables, we divide let's say the x and y axis into sub-intervals, and we pick a typical rectangle from that sub-intervals, whose length is, let's say, delta x and the width is delta y, where delta x is b minus a over m. M happens to be the number of sub-intervals along the x-axis, and delta y is d minus c over n, where n is the number of sub-intervals along the y-axis. Keep in mind the closed interval right here, I should say the closed region, is where x goes from a to b and y goes from c to d. In other words, what we have is the following. So instead of dividing the x-axis into equal sub-intervals, now we're going to go a to b along the x-axis and c to d along the y-axis. And we're going to come up with this rectangular region. And then we're going to divide this rectangular region into so many sub-intervals along the x-axis and so many sub-intervals along the y-axis. So we take one of these sub-intervals that would be a rectangle whose length and width is delta x and delta y. And delta x is b minus a over m. Delta y is d minus c over n. So dA, that means that's like the area element. So this would be like area element is equal to delta x times delta y, you know, the length times width, which is the same as dx dy. So what happens is, so now we have double integral, what? Of fxy dx dy, where x goes from a to b and y goes from c to d over a rectangular region on the xy plane. So what happens is the following. If you divide the xy plane into what? Rectangular subintervals, remember this is a closed region, correct? And you pick one of these elements, let's say a sample point, let's say p x sub ij comma y sub ij. So what happens is when you find a what area of this typical rectangle on the xy plane, and you multiply it by what? The height of that what? That particular point on the xy. So what happens? This quantity right here, it's what? It's height times the area element. So in turns, if fxy is what? Positive continuous function, so this represents the volume. So what you're doing is, instead of adding the what? Areas of these rectangles in what? Single variable function, like y is equal to f of x, what we do here for approximating the value of the what? Double integral in terms of x and y, we add the volumes of these so-called rectangular boxes, or some people call it prisms. So when you what? Continue doing this for every what? Little sub box, you get what? You get a rectangular box, and you add all these the volume of these rectangular boxes. So then you will have double sum. So now this would be like what? Double Riemann sum. Remember, in single variable case, you either had to approximate the definite integral using the left endpoint, right endpoint, or midpoint. In double integral, because you're dealing with the rectangular region here, either you use the upper left corner, lower left corner, upper right corner, and this is lower right corner, or the midpoint of the box on the xy. So there are 5 different ways of approximating a double integral. So remember, I is what? Is I goes from 1 to m, is the number of subintervals along the x-axis. And j goes from 1 to n, which is amount number of what? Subintervals along the what? Y-axis. And p sub what? xij and yij is called the sample point. So you, of all these rectangles, this is like a typical rectangle. Once again, just like the single variable, if the function was positive, then the definite integral would represent what? The area. In this case, if the function fxy is positive, then the double integral computes the volume of the solid, which happens to be below the surface, but above what? The rectangular region. So in other words, you're finding the volume of the solid, which is trapped between this rectangular region and what? Below the solid. Do you see it? So special case, so this would be like special case, and that would be what happens if the integrand for double integral, this guy right here, is equal to 1. If it is equal to 1, then this particular integral, double integral, with the integrand being equal to constantly equal to 1, computes the area of the region R. So it would tell you what the region R is, correct? In case of rectangular region, notice we had what? Let's say 1, let's say dy dx, that would be dA. Let's say what? Y goes from C to D, and what? X goes from A to B. So that would be the same as what? D minus C times B minus A. And that's exactly the area of the what? Of the rectangle, which happens to be going from A to B, what? Along the what? X-axis, and what? C to D along the what? Y-axis, something like this. Do you all see it there? Right? So in other words, if the integrand happens to be equal to 1, what you're finding, instead of volume, you're finding the area of the region. In this case, rectangular region. So the formal definition of double integral over a rectangular region is limit of what? All those heights of those prisms times the area element. So delta A is the area element. Is that right? Element. And then you have to have double sum. Why double sum? Because remember, you're adding what? All those sub boxes along the x-axis and along the y-axis. So this will be called double Riemann sum. And if you increase the number of subintervals both along the x and y axis and let them approach to infinity, that would be the definition of the what? Double integral of fxy, what? Over a closed region. Once again, I emphasize the region has to be closed. Otherwise, what? You cannot evaluate the definite integral. Provided this limit exists, which always does if the function is continuous, then that would be the formal definition of what? Double integral. Case in point, let's just do a problem so we can see how this works, and then we go from there. Suppose you were asked to approximate this, where region R is what? X goes from 0 to 4, and then y goes from -1 to 2. This notation is called Cartesian Product. Basically, it means x goes from 0 to 4, and y goes from -1 to 2. So there it is, -1 to 2 and 0 to 4. And they want you to take m equal to 2. So that means divide the what? X-axis into 2 equal parts. And n as a Nancy, 3, that means divide the what? Y-axis into what? 3 rectangle subintervals. So in turns, you got 1, 2, 3, 4, 5, 6 rectangles. But now they want you to take the lower right corner points of each box. So if this is box number 1, number 2, number 3, number 4, 5, 6, take the lower what? It says, the problem says take the lower right corners. When you do, so what you have to do first, you got to find delta A, which is the area element, and that's delta X times delta Y. Notice delta X is what? Is 2 units. Delta Y is what? 1 unit. So from here to here is 1. From here to here is what? 2. So delta A for all these 6 boxes happens to be 2. You could also check how to get delta X if you can't see that by inspection. Use the formula and you get the same answers. Once again, the region is closed, rectangular region. So now what we do is what? Multiply the height of the function, which happens to be this guy. So this is the height, which is 1 minus, in this problem, 1 minus xy squared. Evaluate it at these lower right corners and multiply by the corresponding area. So height times area gives you what? Volume. Provided, once again, I repeat, provided this function is positive over what? This region. Turns out in this particular case, function is not positive, so we are not finding the volume. We're just strictly following the definition, which is evaluating the function at each of these lower right corners, multiplying by the area of each of these what? Boxes on the x and y axis. So evaluate the function here, here, there, and up here, and multiply by delta A. Delta A for all of these boxes happens to be 2. So you got 1, 2, 3, 4 of these guys. So what? Add up the product of the area of these boxes times the value of the function at those points. In this case, you were told use lower right corners. And lo and behold, when you do the math, you get negative 12. Remember, I told you this is not a volume problem because the function is not positive over this region, is not. So it's okay to come up with a negative answer. In this case, what we have is Fubini's theorem. Giotto Fubini was an Italian mathematician, and he proved that what? If you are on a closed rectangular region, so that means the limits of both integrals happens to be constant, then the order how you integrate this, it doesn't matter. In other words, you can integrate or perform this double integral going dy dx or going dx dy. Those are called the orders of what? The integrals. So if you go dy dx, you gotta go y goes from what? C to d, x goes from what? A to b. Now if you switch the order of integration, that's what that's called. So you go dx dy, then you gotta go x goes from what? A to b, and y goes from what? C to d. Mr. Fubini proved that what? If the limits of integrations are constant, meaning you are on a closed rectangular region, which in this section we're going to have general region, doesn't have to be rectangle anymore, you can switch the order of what? Integration, and lo and behold, the answer comes up the same. So in this case, the order does not matter, provided you are on a rectangular what? Closed region. Do you see it? In other words, if I was going to what? Evaluate this and find the exact value, which we will learn how to do this, and you go through the computations, what do you know? The answer comes up to negative 12. So what do you know? The approximation was right on the target. So we hit the bullseye. Notice the exact comes up to 12 as well. So sometimes the question is, what happens if the what? If the function fxy is constant, like 5. What exactly this guy represents? Well, this guy represents what? 5 is positive. So therefore, this computes the volume of a what? Rectangular box whose length goes from 0 to 2, width goes from 0 to 3, and the height is constantly 5 units. So what happens is, if you perform the what? Double integral, you get 30. But if you recognize that this, because it's constant, so it, computes the volume of a box whose height is rain or shine 5 units, and the length is 0 to 2, width is 0 to 3, you could have just multiplied 3 by 2 by 5 and get the same answer, which is what? 30 cubic units. Do you see it? So that will be 3, the length, the width is 2, and the height is 5. So the volume is what? Length times width times height, and lo and behold, you have it. Do you see it? On the other hand, if the what? The integrand z is equal to 1, well, you can think of this as it has two interpretations, but the interpretation the textbook usually get is you find the area. In other words, you're finding the area of a box whose length is 2 units and the width is 3 units. And lo and behold, notice 2 times 3 gives you 6, and that's exactly the value of this integral gives you. However, there is a different school of thought, which means This could be also a box whose height is equal to 1. In other words, the volume is what? 6 cubic units. So magnitude-wise, we get the same answer, but unit-wise, we get what? Cubic units for volume, but square units for what? Area. As I said, in most of the textbook in calculus, they take it that if this integrand is 1, you are finding the area of the region R. In this case, the R is a rectangular region whose length and width is 2 and 3 units, respectively. Okay, so now basically what we gotta do is, let's say we like to evaluate this integral, let's say by exact way. So the way we do it goes something like this. Just suppose we were asked to evaluate, okay, this double integral, and I'm going from, what was it? Say -1 to 2, and I'm going 0 to 4, 1 minus xy squared, and I'm gonna take what? dy dx. Later on, I'm gonna do the same problem, but switching the order. And I like to show you that if the limits are identical, constants, then what? You get, what do you get? You get same answer. Who said that? Well, Mr. Fubini proved it. Here's what we do. To evaluate this, find the exact value, what you do the double integrals from inside out. First, you evaluate or integrate this guy with respect to y. So that means x's are kept constant. So what happens is, so this integral sign stays, but this guy with respect to y is y. X is constant, so it goes for the right. So this is y cubed over 3. And I'm going, y goes from what? -1 to 2. I still have dx. So using the fundamental theorem of calculus, evaluate this first as 2. So that would be like, let's say, 8/3 x. Then minus at -1, which is negative. I believe that would give you positive x over 3. And now we are back to single variable, don't we? So what would this guy be? Well, this would be like 0 to 4, 2 minus minus plus 1, which is 3, minus 8/3 x minus what? X over 3, that's minus, and that's minus, so that would be minus what? 9 over 3, which is 3x, and that would be dx. So if you evaluate this, you get 3x minus 3/2 x squared. Is that right? From 0 to 4. So that's 12 minus 3/2, 16. So that's 12 minus, what is this? 24, which is -12. Do you all see it? And that's exactly what we had when we what? Did it the exact way. But I didn't show you how. Now you see how I got it. On the other hand, if I do this double integral, perform this double integral with respect to x first and then y later, we should get the same answer, correct? The only problem is now y's are kept constant. Do you see it? So this guy stays. This guy would be x minus the y squared goes for the right, but antiderivative of x is x squared over 2. But now you got to evaluate this between what? 0 to 4 for x. But then you still got dy to take care of. Do you see it? Okay, so using the fundamental theorem of calculus, so you go, hey, this is 4 minus what is that? 16 over 2, which is 8y squared minus 0. So that will be minus what? 0. Is that right? So that really doesn't matter. So if you don't mind, let me just erase all this. And then lo and behold, you are back to single variable function. Just like first semester calculus. So now you integrate this guy with respect to y as 4y minus 8y cubed over 3, but y goes from -1 to 2. So using the fundamental theorem of calculus, so this would be like 8 minus, what is that? That's 8, that's 64, 3 minus, that's -4, that's positive 8 over 3. Do you all see it? So 8 plus 4 is 12 minus, that would be what? 56, is it? And that is what? Let me just, yeah. Okay, so now if you work this out, that's 3. And that would be 36 minus 56, which is negative, what, 20? Is that right? Let me just make sure. That's 8, 64. This guy is minus 1. And this guy is positive 8/3. So that's positive 12 minus, okay. And so, okay, let's see, minus, all right. Okay, sorry about that. This is supposed to be minus 72 over 3 when you, add these two fractions. Sorry about that. And then when you find the least common denominator and all that good stuff, notice you still get what? -12, which you're supposed to. Mr. Fubini proved that. So the idea is now, so we get to find the volumes of solids using what? Double integrals. One of the problems which is my favorite is this guy right here. The volume of a solid bounded by the surface z is equal to 16 minus x squared, which happens to be a what? Cylindrical surface, and the plane parallel to the what? XZ plane, perpendicular to the y-axis, which is y equals to 5. And this is how it looks like. Here's the cylindrical surface. And here is what? Y is equal to 5. So intersects what? This cylindrical surface at this curve. So this curve is the curve of intersection of this surface and this plane. So the formula to find the volume is double integral z top minus z bottom times the area element. Okay. So this would be the height. And this would be what? The area. Height times area gives you the volume of a typical what? Box. So the typical box would be something like this. Do you all see it? Right? So guess what? Z top, the top surface is this cylindrical surface, which is 16 minus x squared. The bottom is what? Is the floor, which happens to be 0. So that's the floor. The bottom of the surface is sitting on the floor. So the bottom is 0. So z top minus z bottom is 16 minus x squared minus 0. And as you can tell, x goes from 0 to 4 and y goes from 0 to 5. If you do the math, you would end up with 640 over 3 cubic units for what? For volume problem. So that would be the volume of this surface bounded by this cylindrical surface and the plane. Thank you.